So today we'll look at 2 to 6 invert binary tree. Um, so given the root of binary tree, invert the tree and return its root. So what we need to do is here 42713 is given like this. So we have to create a mirror, like change the places of these guys. So how will you do it? Okay. So basically, okay. So starting from the root node. Okay, so what my intuition is, like, you can come down and like till the leaf node, and then once you got the null, then you can return, and then you can point the current root dot left to the current root dot right, the left that was returned. Okay, so okay, okay, so yeah, my intuition is like that only. Whenever you'll find out any leaf node, you will return it, and then you will assign the root dot left to right and right to left, and then you will return from there, and then similar thing will happen um, on the upper level. Okay, so what I'm talking is, if root equal to null, then we return root. Okay, and if so let left is equal to invert tree, will send the first root dot left. Then once we are done traversing root dot left, we'll send invert tree root dot right. And once we are done traversing both, then what we have to do is root dot left root dot left will be right. We'll point at right. And do we need to switch the, okay, because when this left would be returned back, yeah, I guess we don't have to switch the values, we have to switch the reference. So root dot right will be left, and yeah, that should do it, and that will go above. Okay, yeah, it did not, it's undefined. So what I'm doing is I'm sending back null. Null comes in, then I set a root dot left to the right and root dot right to left. Then I send back, then I return. So yeah, we have to, I guess, return the root. Return root. Yeah, we were not returning anything. So yeah. So now it will work. Yeah. Okay. So cool. Submit. Yeah, it's working. So last time I did it in this way. So there might be a follow-up question where they will ask us, uh, how would you do it? So we were able to do it in 4 minutes. Let's see how. Okay, let me first of all draw this guy. The question asks you, okay, this Miro app is not behaving properly. Okay, so I have 4, 2, 7, 1, 3, 6, and 9. Okay, let's go here. Okay, we have this tree in front of us. So what we need to do in order to invert this is that my logic was to um, go down the left side of the tree. Like we have to traverse both the sides. So what we'll do is we'll go down the left side first, and as soon as we hit null, we return this null to the left. We'll store this in left, and this also will be null, right? So this will be set to null, right. Let's call it R and L so that we are not eating up more space. Okay, let's keep it like this. L and R. Okay. So yeah, what we do is then we got the values of the right and left. Now we change the reference of this current. Once we return this right and left, we have the access to this guy, right? So we change the reference to root dot left to right and root dot right to left. So that's so this will get inverted like so yeah, that's the whole logic. So from bottom we are going to do the same thing over and over again, and then that's how it will get uh, inverted. So let's see. So this got inverted in its place. So yeah, let's clear this out. We don't need this. Okay. So this guy is inverted, right? This one. So now that we know this guy will return in left. We'll have this guy, and then okay. So left part is done. So we come to the right part. So once we come to the right part, this thing again happen null. This will get inverted, and then we'll invert these two guys, and this will be returned, and this will be stored in right. So once we got this left and right, then we can invert these two also. The same logic applies to every node. So we send this two after inverting its children, and then once we have the topmost layer left, we need to find root right of this guy. So we go here, we see there is another node, then we traverse the left of it, then we see there is another node 6, and then we see null, then we return, and then we traverse the right, return, invert this, and then send back left. Then we see there is a right, then yeah. So so yeah, we traverse this guy, this is null, we invert this, we send this guy in its right, we invert this, we send this guy up, then we invert this too, and then finally we send this root back. So, oh, sorry. So finally, yeah, we send this root up. Hopefully this was clear. And I guess the time complexity of this is often and the space is also of n, or probably in terms, in these binary tree term, it is called of h, which represent the height of the tree. Yeah, because of complexity, since each node in tree is visited only once, the time complexity is O(n), where n is the number of nodes in the tree. We cannot do better than that, since at very least we have to visit each node to invert it. Because of recursion, O of h function will be placed on the stack in the worst case, where h is the height of the tree, because of h is, okay, I don't know what that sign means. O of n, the space complexity is O of n as well. Alternatively, we can also solve the problem iteratively in a manner similar to breadth first search. So yeah, that is something that we can explore. Okay, so in breadth first search, we always traverse in in a, you know, in like first, like level by level, 1, 2, 3. So my idea behind this would be, we traverse the node first, and then when we are traversing this the second level, then we need to make sure that root dot left, like we have to invert the positions, right? Basically, yeah. Okay, we can do that. So let's try to solve it in breadth-first search manner. So this would be our base condition. If root equal to null, then we simply return root, which means null. Okay. So in breadth first search, we use Q, first in, first out, right? That's what it means. Let Q is equal to an empty array in which we put root, and then while Q dot length, like, which means it's not empty, we have to keep traversing. Okay, so for every level we need to check the size of the queue, which defines the current size of the queue, like till what point we have to run, keep shifting, like keep removing the element from the first, from the queue. So this size gives us um, the appropriate measure, like till what point we need to remove the elements. So yeah, so what we can do is, we can have a for loop or while loop, whatever suits. If I is equal to c, let's do this. I is less than size, I plus plus. Oh, sorry. So let's do this, and then we shift the current node. So current node would be q dot shift, which gives us the first node in the queue, like that. Yeah. Okay, so we have the node in front of us. So what we can do is, we can have let left is equal to null and right is equal to null, and if node dot left is there, we can put node dot left in node dot left, and in left, and then okay, and then we can also push this node dot left onto the stack, and if node dot right is there, then right is equal to node dot right, and we can push this onto the stack node dot right. And what we can do is we can basically invert those positions. So node dot left is equal to right, and node dot right is equal to left. Okay, once we do this, yeah, we know for sure we have. Okay, so yeah, so that should do it, and then we can return our root finally. I hope I have done this right. Yeah. Okay, so that was also accepted. Cool. Let's see, time complexity would be the same for, but in this, yeah, O of n and O of n, because we are storing Q. Yeah, for both of them, we are doing that. Okay. Yeah, that's right. Okay then. So what we can do is, so in what respect they were using temp? So they pulled this current and they put the temp here. Then, okay, yeah, I see what they did here. So we don't need this guy. Yeah, even if we are just having, but we do need node dot left, right. Yeah, so this is also good, I guess. Yeah, no need to change it according to this. So okay, that's all, guys. Let's see what we can do and then do in the next. The next one would be maximum depth of binary tree. So let's do that. Cool. Pretty interesting question. Let's see how many times it's been asked. Okay, not been asked so much, but yeah, one of the first starting questions of binary tree. Okay, cool. I'll stop this stream. Okay, thanks. Bye.